So far we've seen that carboxylic acids can make acid chlorides, they can make esters, they can make amides. In the next reaction we're going to see that they can also make acid anhydrides. So anhydrides are formed from the dehydration of two carboxylic acids. If I take a carboxylic acid and I react it with another carboxylic acid in the presence of heat, in essence, I'm dehydrating it. So I lose water, and the remaining oxygen there then attaches to the other carbonyl. That's a very simple way of thinking about it, but sometimes, we have to think about simple ways of putting things together. And that's certainly one way of thinking about it. So we lose water in the process. An example of this is if I take acetic acid and I heat acetic acid up. This is a great way of making acetic anhydride. So I need two equivalents of acetic acid. I heat it up and I produce acetic anhydride plus water. Another way is if I take a dicarboxylic acid. So in this case, we have phthalic acid. And if I heat up phthalic acid at 200 degrees Celsius, I get my anhydride, and this is called phthalic anhydride. Now, the best way of making acid anhydrides is actually not from carboxylic acids, heating them up. As we've seen in the past, when you heat something up at a high temperature, a lot of times you get decomposition. So the best way of making acid anhydrides is actually not from carboxylic acids, it's from the carboxylate with an acid chloride. Notice we can deprotonate a carboxylic acid to get the carboxylate. We can make acid chlorides taking a carboxylic acid, reacting it with thionyl chloride, and so now I have my carboxylate, I have my acid chloride, and I can generate essentially any acid anhydrides. In the what we just talked about, reacting two carboxylic acids, basically you have to have a carboxylic acid that's undergoing a dehydration, and the R groups are the same. With this method, you can see that the R groups can actually be different. So you can make asymmetrical anhydrides in this fashion. And the way this happens is the carboxylate's a nucleophile, and we will be seeing a lot of reactions of acid chlorides later on, but acid chlorides are electrophiles. So they'll undergo addition elimination reactions, they're called, and so the oxygen attacks that carbonyl. We produce a tetrahedral intermediate where the oxygen has a negative charge on it, and that tetrahedral intermediate can then reform a carbon-oxygen bond, and chloride comes off, right? And we're going to see this type of reaction occurring again and again and again. So you have to become very comfortable in thinking about these tetrahedral intermediates and what's going to happen to them. Here I have a tetrahedral intermediate. Oxygen then reforms that carbonyl, which is a big driving force for a lot of reactions of acyl groups, and displacing that chloride, and of course we generate our anhydride. Now, we can also get carboxylic acids to react with some organometallic reagents, namely organolithium reagents. They don't react very readily with Grignards because they're acids. So acids with a Grignard you're just going to get protonation of the Grignard. Now, this also happens with the organolithium, but Grignard reagents won't react with the carboxylate that's formed. So carboxylic acids will actually react with two equivalents of organolithium. And of course that first step is a deprotonation, which I'll show in just a little bit, and then the second step is actually attack of the organolithium. We've already seen this reaction, but I just want to bring it to your attention again that you could take a carboxylic acid and react it with two equivalents of organolithium. And again, I'll talk about the mechanism of this, but the key is that you produce ketones. So carboxylic acids can make ketones using organolithiums, right? So one of the things that we're going to be seeing a lot of reactions here. Make sure you try to categorize them. Carboxylic acids can make esters, carboxylic acids can make amides, carboxylic acids can make acid chlorides, carboxylic acids can make anhydrides, carboxylic acids can make ketones. And of course the reagents that will get you to those particular functional groups. So here I have a carboxylic acid reacting with propyllithium followed by an aqueous workup, and I get a ketone from this. And the mechanism of this is fairly straightforward. The first step is we have an acid, we have a base. We get proton transfer. And we generate carboxylate. So the lithium carboxylate plus our alkane from the organolithium. So now a second equivalent of organolithium comes in, and it is a good enough nucleophile to react with the carboxylate. There are many nucleophiles that aren't, but organolithium is one of them. So it can attack the carbonyl carbon, and we generate a dianion. So remember, we talked about this already, but this is a dilithium dianion. And when I treat that dianion with water, I form a geminal diol, and that geminal diol undergoes a conversion to a ketone because there is an equilibrium between the ketone and a geminal diol in water. But that equilibrium lies toward the ketone over the geminal diol. So this is a great way of making ketones. And that's the key, ketones. We're making ketones. Now, if you think about carboxylic acids, you might envision that you could lose carbon dioxide. This would be called a decarboxylation. And the product of that would be an alkane, possibly. This is easier said than actually done, but there are some reactions in which decarboxylation can occur, namely with two different types of carboxylic acids. One is called a beta-keto acid, and the other is called a 1,3-dicarboxylic acid. So these two types of acids can undergo decarboxylation. And the key is, number one, recognizing what a beta-keto acid is and what a 1,3-dicarboxylic acid is. So this is a generic structure of a beta-keto acid. Remember, I talked about the lettering or labeling of carbons coming off of a carboxylic acid. And so if you take a look at that numbering, right, the carbon attached to the carboxylic acid is called the alpha carbon, and then the beta carbon is attached to the alpha carbon. Notice in this beta carbon has a carbonyl coming off of it. And that's where we get the beta keto, right? It's a ketone, a beta keto acid. Now, 1,3-dicarboxylic acid looks like this, right? So instead of numbering it alpha beta, we could number it 1. We could number the carboxylic acid 1. The carbon connected to it would be 2, and the carbon connected to it would be 3. All right, so these are called 1,3-dicarboxylic acids. But notice the similarity between the structures. The key is that you have a carboxylic acid, and then on the beta carbon, so the carbon on either, you can think of it as the beta position or the 3 position, has a carbonyl associated with it. Now, 1,3-dicarboxylic acids are often called malonic acids, and there's a whole bunch of derivatives of malonic acids, but malonic acid itself is 1,3-dicarboxylic acid. Malonic acid is found in nature, and oftentimes things things can break down, and our bodies can generate carbon dioxide in the process. All right, so let's think about the mechanism that is involved in decarboxylation, and it's actually a very well, it's not a very long mechanism, but you have to really be careful about where the arrows are going. And it is an intramolecular enol formation. So we're going to be forming an enol that's going to tautomerize to a ketone. And if I look at, I'm going to use a beta keto acid. I could do this for the 1,3-dicarboxylic acids as well. I'm going to redraw this, and I'm going to rotate about the carbon-carbon bond of the between the carbonyl and that alpha carbon. And I'm simply going to redraw it like this. So notice I've drawn the OH going up and the carbonyl oxygen pointing down and to the right. And the reason for this is because, and this is certainly the key for decarboxylation, we have a stabilization from the carbonyl on that beta carbon to the carboxylic acid. So much so that we can actually donate a pair of electrons from that carbonyl to the hydrogen. So it's undergoing proton transfer. When it does that, the electrons from that OH bond swing in to form a pi bond with the carbon. And now, instead of having the carbonyl pi bond, the electrons from that swing up into the oxygen, instead, we have the carbon-carbon sigma bond breaking and forming a pi bond between the carbon, that alpha carbon, if you will, and the beta carbon. The result looks like this. So now that carbonyl oxygen is protonated, it's an OH. I have a double bond, and so I formed an enol. And also notice I generate carbon dioxide in the process. Now that enol, we know, tautomerizes to the ketone. So this is another way of producing ketones from carboxylic acids. Notice, unlike the organolithium reactions with carboxylic acids that produce ketones that have more carbons, decarboxylation of a beta keto acid or malonic acid produces a ketone that has fewer carbons in the chain. So here's an example of a beta keto carboxylic acid. The reagents necessary for this is heat. So it's actually very easy to decarboxylate these types of things, and malonic acids are actually relatively unstable, as are beta keto acids. And so what, to kind of visualize what's going to happen here is you can think about that carboxylic acid. The CO2 is coming off. The hydrogen then basically replaces where that CO2 was located, and so we get this, right? We've formed our ketone in the process. But if you count the number of carbons that we started with, 1, 2, 3, 4, 5, 6, 7, 8, we end up with a ketone that has 1, 2, 3, 4, 5, 6, 7 carbons attached to it, because that CO2, we've lost one of the carbons in the process. Now, there are other decarboxylations. One of them is that if we take an ester or an amide of carbonic acid, we can also get decarboxylation. So carbonic acid looks like this. H2CO3 is carbonic acid, and carbonic acid in and of itself is relatively unstable. It produces carbon dioxide and water. This is what we put in soda to make it bubbly, and of course it's in equilibrium with water, and that equilibrium gets shifted to produce carbon dioxide. So that's how we carbonate our beverages. So if I think about carbonic acid undergoing a decarboxylation, I can think of an ester of carbonic acid undergoing a decarboxylation as well. And so we generate CO2, and we also can generate alcohols in this fashion. So the key is that we are making alcohols from the esters of carbonic acid. Now likewise, we can take an amide of carboxylic acid, and these are called carbamic acids. And carbamic acids, if I heat them up, will produce carbon dioxide and amines. So you see that when we decarboxylate carbonic acid esters or carbamic acids, we can generate alcohols or amines, respectively. Now, normal decarboxylation doesn't occur using other types of carboxylic acids other than the beta-keto acids or the 1,3-dicarboxylic acids. However, there are certain carboxylic acids that can be decarboxylated by electrolysis. And this is called the Kolbe electrolysis, named after Kolbe, who discovered this type of reaction. And essentially, what you're doing is you're taking the carboxylate, so you're deprotonating the carboxylic acid. You take the carboxylate, you apply an electric current through it, and you essentially dislodge an electron. So notice I have now my carboxylate it's a neutral radical species, and I showed one of the electrons, that one lone electron up there, as a red dot to signify that I've lost an electron there. Now, what happens is that red dot, so we're now undergoing a radical reaction, so that red electron moves in and it forms a pi bond with one of the pair of electrons from the carbon-carbon bond to generate carbon dioxide, and the last electron then goes to that carbon. So what I end up with is a radical, a carbon or an alkyl radical plus carbon dioxide. So carbon dioxide, it goes away as a gas, and now I'm generating lots of radicals in the process, and those radicals can react with one another to produce alkanes. Carboxylic acids can produce alkanes in the presence of electricity. Okay, so that's the key. Electricity, carboxylic acids produce alkanes. Now, so what are the products going to look like? Well, keep in mind that when I apply a current through that carboxylic acid, I lose carbon dioxide. So when I'm looking at my carboxylic acid, notice I have, I'm dealing in this particular example with butanoic acid, and I'm going to lose CO2 in the process. So I'm losing a one carbon on my chain. So two of these are going to react, and I have a 3-carbon chain that I'm going to then react with another 3-carbon chain. And so in the process, I get a 6-carbon chain. So I produce hexane in this reaction. And the last reaction in this section is called the Hunsdiecker reaction. And the Hunsdiecker reaction essentially forms alkyl halides from carboxylic acids. Now, what we do is we start with a silver carboxylate salt, and we react it with bromine. And in that process, the carboxylate is a nucleophile. Bromine we've seen behave as an electrophile. What we generate is a This is called a hypobromite, where you have that oxygen that has a bromine bond associated with it. And of course, we get bromide as a salt. Now that hypobromite dissociates. The oxygen-bromine bond is very weak, so with any light whatsoever, it's going to dissociate. And notice what it produces. It produces something that's very similar to what we saw in the electrolysis of carboxylic acids. So what happens next? Well, you know what happens next. We're going to generate our alkyl radical. And so we generate our alkyl radical plus carbon dioxide plus bromide. All right, now the next step is that the alkyl radical reacts with the hypobromite. So this is the different aspect of this reaction versus electrolysis. In electrolysis, we don't have hypobromites. In the Hunsdiecker reaction, we have a lot of hypobromate present. And again, that hypobromite can dissociate. All right, so what happens in that dissociation? Well, the radical reacts with bromine, and I produce an alkyl bromide. Again, notice I produce that funky carboxylate radical as well. So the key is that I'm producing alkyl bromides. I can take a carboxylic acid and treat it with a silver hydroxide to produce silver carboxylate. Then treat that silver carboxylate with bromine, and I can produce an alkyl bromide. Again, carbon dioxide is leaving, so be very wary of your carbon chain length. Now, obviously, I'm also generating that radical, and that radical can then recycle and produce carbon dioxide and another free radical, and then that free radical can react with another hypobromite, and the reaction can continue on and on and on. So let's look at an example. Here I have my silver carboxylate salt. Again, I'm using the salt of butanoic acid, reacting it with bromine. And again, the carbon dioxide is going to come off, right? So I have to count the carbons after the carboxylate. 1, 2, 3. Then bromine adds to that. So I'm going to get propyl bromide in the process. And that wraps up this particular section of carboxylic acids. We've seen a lot of reactions of carboxylic acids and what they do. We've seen that they can make acid chlorides, they can make acid anhydrides, they can make esters and amides, they can make ketones in various ways, they can make alkanes, they can make alkyl halides. And it's certainly a good idea to write these things out, write these reactions out to get them down packed and to get the reagents down packed as well.